We will discuss torque on a current loop in this lecture. Let's study the forces acting on a rectangular loop with side A and B carrying a current I and is located in a uniform magnetic field. Let's assume the magnetic field B is parallel to the plane of the loop. Because for side 1 and 3, the current is in parallel with the magnetic field, so no magnetic force acting on side 1 and 3. If we use the right-hand rule, we'll find out the magnetic force acting on side 2, pointing out of the screen, which is pointing into us. The magnetic force acting on side 4, pointing into the plane. So now let's change our perspective of the situation. Let's imagine we are looking at it from the position of the eye and then look at it along the direction of the rotational axis, which is represented by this red line here. So if we change our perspective, we'll find the force acting on side 2 right now pointing up. The force on side 4 pointing down. Those two forces pointing in opposite direction, but they are directed along different line of action. So they are not going to give us a net force, but they are going to give us a torque tau. Let's calculate what would be the torque tau. The lever arm for both F2 and F3 is half of the length of side B. So the torque by F2 is F2 times B over 2. The torque by F4 is F4 times B over 2. With some calculation, we find that the total torque is I times A times B times magnetic field. A times B for the rectangle would be the area of the rectangle. So we found out actually in this configuration, the total magnetic force will give the loop a torque which equals to B times I times A. This maximum torque would be valid only when magnetic field is parallel to the plane of the loop, and then the torque will make the loop rotate. If the current direction reversed, then the direction of the torque would reverse as well. So the rotational direction would be counterclockwise in the event we reverse the direction of current. If the magnetic field makes angle theta with the norm vector of the loop, which is vector A in the graph, then we can calculate the torque in this case is given by B magnetic field, I current, A area of the loop, and sine theta. For loop current inside the magnetic field, the total torque equals B times I times A times sine theta. Even though we derive it using a rectangular loop, actually this is a more general equation applies to any shape of loop. And if the coil has n turns, then we simply need to multiply n to our equation to calculate the total torque. So which allow us to define a magnetic momentum, which is a vector quantity. It's pointing in the same direction as the normal vector of the loop. And then the magnitude of the magnetic momentum is I times A times N. I is current, A is area of the loop, N is how many turns we have. So now we can simplify the equation and write net torque to be mu times B times sine theta. Let's study how electric motor works.
The torque in a DC electric motor is created by magnetic forces exerted on the electric current carried by the rotating part of the motor. In this virtual model, the flow of conventional current is represented by the moving red balls. The magnetic field is represented by the blue lines. The current loop experiences a torque due to the offset forces on the top and bottom sections of the loop. The forces on the front and back segments of the loop exactly cancel, so they do not contribute to the net torque on the loop. The battery that drives this motor produces a constant voltage which can only drive the current in one direction. However, the motor loop would get stuck lined up perpendicular to the magnetic field if its current never changed direction. A clever mechanical connection called a commutator allows the single direction battery to supply a current to the loop that switches direction every half rotation.